So hi. So we're happy to have George Kellaris today to talk about accessing data while preserving privacy. Looks like it's going to be interesting. George is a postdoc in CRCS for a year, and he will stay with us for the next year. He's been working on privacy, defense of privacy, a lot of implementation stuff. George did his PhD in
Hong Kong University of Science and Technology.
Hong Kong University of Science and Technology. And since he came here, he was involved in the Privacy Tools project, involved with work with many of us here in computer science and outside computer science. He's doing some very interesting stuff in his work. And I think that's it for today. Yeah, he will now present his work.
Thank you very much, Kobe. So thank you all for coming. I'm going to present you the work we've been doing the past few months with Georgios from Boston University, Kobe, and Adam O'Neill from Georgetown University. So the title of this talk is Accessing Data While Preserving Privacy. We're going to talk about querying encrypted databases. So let's see the setting. Assume that we have a bank that keeps the records of its clients or customers. So each record might have a lot of attributes like the name, the address, the number of the accounts they have, the credit cards. And the bank wants to efficiently query these records, to retrieve these records, using a subset of its attributes. In order to do that efficiently, it will create an index on some of the attributes, and which will have some pointers to the real records. So when we want to find the clients that have as a first name Gina, we just have to follow the pointer and retrieve the records. What are some types of queries? So let's say that we need all records with the client's name Gina. This we call a point query, because what we actually want is we want to retrieve the records that have a specific attribute equal to a value. Then we might have another type of query. Let's say we want all the records of the clients whose age is between 32 and 52. We will call that a range query. In this case, we will go to the age attribute, and we're going to find all the values that are between these two numbers and retrieve the records. Another query might be that we want all the male clients of the bank. In this case, we are talking about a one-way attribute query. And if we want the male clients that are not married, then we have a two-way attribute query. Yes?
How are you differentiating between a point query and a one-way attribute query in that they're both sort of looking for explicit matches on the field?
So in one way, we can consider the attributes as a binary. Okay?
Are you assuming that names are unique?
They don't have to be unique. So a pointer might point to a lot of records, or we might have the same attribute here with one pointer. It doesn't matter. This is how the indexing happens in the database system we use. OK, so this database might grow really large. So the bank doesn't want to deal with it anymore, but still wants to retrieve records. So we can use a third-party server, the cloud, which will keep the data for the bank, and then we will query the cloud instead to retrieve records. So the problem is that we cannot trust a third party with our sensitive client data. So how can we do that? We can use cryptography, of course. So the questions are, OK, if we want to share our data, to upload our data, outsource them to a third party, is this efficient? Can we retrieve the records efficiently as they are on our side? And is this secure, most importantly? So there are crypto solutions in order to be able to outsource our database and encrypt it. We can use oblivious randomized access machine. We can use fully homomorphic encryption, PIR. And we can have our data encrypted on the third party and query them. The problem is that all these solutions are not very efficient yet. So current works usually try to implement systems that are secure and practical. In order to do that, they do not use these strong notions of cryptography, but some relaxed ones, like order-preserving encryption. And by using this type of notions, we can query the data very efficiently while maintaining a level of security which is considered to be reasonable. Examples of this system is CryptDB, Cypherbase, and also on top of that, some systems of Microsoft or Google are built with the same principles. However, there are many attacks on these systems. Some recent ones, they managed to reconstruct the whole database. So we can see that there are some problems with these systems. However, these attacks are very specific to these implementations, and they make some assumptions about the data distribution. So the question is that how can we really tell about the security privacy these systems offer? Because until now, this is not well understood in the literature. In order to do that, we're going to have a generic approach for the outsourced database system setting. Our goal is to find the privacy efficiency trade-offs of these systems by exploring an implementation-independent model. In order to do that, in this talk, we are going to see some basic leakage channels, which we call access pattern and communication volume. Then we're gonna see some reconstruction attacks for optimally efficient outsourced database systems, which we find in the literature. Then we're gonna present how we can have differentially private storage in order to deal with these attacks. And we're gonna present two cases. The one is going to be in the atomic storage model, which we're going to see later, which is what is used right now. We're going to show some bounds in the efficiency. And then we're going to present a general model which enhances ORAM with differential privacy. We have to note here that we only consider static databases for this talk. We don't have any updates. And we consider that the indexed attribute is a sensitive attribute, and we don't want the adversary to be able to infer anything about that, like the distribution of the records on the indexed attribute. So let's see the atomic storage model, how it works. So we want to outsource our database to the cloud. So what the bank does is that it generates a key, encrypts each record separately, creating a ciphertext. Then it will encrypt our index, creating a data structure, and will upload everything to the cloud. Then, if we want to ask a query, we're going to encrypt the query so no one knows what exactly are we asking for. And we're going to send this query to the cloud. And by using the data structure and this encryption of the query, we can find which ciphertext, which records we need to retrieve. So let's say we need these two records. So we retrieve these two encrypted records, and using the key, we are going to decrypt them. Now, if we want to ask another query, we're going to encrypt it, send it to the server, again, use the data structure, and we're going to retrieve the record we need. In this case, we retrieve the same encrypted record. So the one issue with this model is that it leaks the access pattern. So the access pattern is that an adversary, let's say the cloud or someone in the middle listening to the channel, can tell which encrypted records we retrieve. Of course, he cannot decrypt the records, but he can tell if the same record is returned twice or for another query. But in general, more information can be leaked. An adversary would be able to tell if the same query is asked twice, if it is the same encryption of the query. But we will not consider that. We have a more general model where we don't consider this more information. Also, we're going to assume that the system is optimally efficient if the stored records that are in the cloud have the same cardinality as the original records we had. And we're going to say that it's optimally efficient in terms of communication if when we ask a query, the number of records we retrieve, the encrypted records, is the same as the required ones for answering this query. All current systems that exist, like CryptDB, they are efficient, and they assume the atomic storage model. But in general, we can also have systems that keep more copies or encryptions of the same record, or also use some fake records. Also, we can assume that some systems may return more records than just one and still be in the atomic model. Now, let's see what is a reconstruction attack on the optimally efficient systems. So conceptually, the information we have is like that. So we have a domain. In this case, let's say, is the account balance of the clients in the bank. And for each value of the domain, we may have a record, which means that a certain client has this account balance. So this information is not visible to anyone. Only bank knows that. So we don't want this information to be leaked, because this is sensitive information about the distribution of the clients over this domain. So a reconstruction attack will try to rebuild this information by just observing the queries. And although we cannot tell about the privacy of these systems, if we can have this type of attacks, this means definitely that we are not secure or we are not private, that there is a problem there. So we're going to consider range queries. So remember, a range query in this case will ask for the client records that have account balance between 20,000 and 50,000, let's say. We're going to retrieve these 3 encrypted records. And we're going to assume a weak adversary who only knows the domain size, the values of the domain, and he's trying to find the distribution. He doesn't know anything about this distribution. He cannot control the data or the queries. He doesn't know what queries are asked. And he only knows that these queries are drawn from a distribution. So he knows the query distributions that the bank is asking. And we're going to consider that a reconstruction attack is successful if we either get this distribution depicted here or the mirrored version of that. We're going to consider that these are the same. So let's see how we can use the access pattern information in order to reconstruct the distribution of the records in the domain. So in this case, first of all, the adversary will try to recover the order of the encrypted records. So the adversary can see the ciphertext, right? So he can have information like that. He knows that we have 5 records in our data. What he wants to do first is to recover the order of these records in the domain, not the positions. In order to do that, it suffices to retrieve t to the power squared log t queries, where t is the size of the domain. And by doing so, he will have different subsets of records. So if we use the largest query, which includes all the records, he can tell how many records we have, and their ciphertext. And by using any other subset which one record is missing, he can infer that, let's say, C5 must be either in the rightmost position or the leftmost position, that it's in the side. So let's say that it assumes that C5 is on the left. Then all he has to do is to observe queries, subset of return records, to see which record comes together with C5. So let's say that we have this query, which includes C3 and C5. Then he can infer that C3 comes after C5. There is no other record in between, because we have a range query. So he reconstructs that. And then by retrieving a query which has C1, C4, and C3, he can tell that after C3, we probably have C1 and C4. And C2 is at the end. So in this case, we have the mirrored version, but it's still OK. Now, if our domain was dense, if we have at least 1 point per position in the domain, we are done. We have reconstructed the distribution of the records over the domain. But if we have some empty spaces, like in this example, then we have to do more work in order to find the exact position of each record. In order to find that, we're going to need more queries. And the idea is that, let's say that we already know the position of C2. Then if we divide the number of queries that include only C2 by the number of queries that include both C2 and C1, we can observe that this ratio gives a value which is unique for every position of C1 after C2.
So you're assuming that the queries are just asking for uniformly random subsets?
Yeah.
Uniformly random intervals?
Yeah, of the domain. Okay? So in order this ratio to be accurate enough, and assuming a uniform distribution of the queries, it suffices to have t to the power of 4 queries in order to find the exact positions. And we can also show that this is the worst case. So as we've seen, access pattern leaks a lot of information, and we can design attacks that are efficient and reconstruct all the information exactly. So an idea is maybe we can use something stronger as a cryptographic tool in order to hide the access pattern. So the adversary cannot cannot see the ciphertext of the records, and he cannot tell if the same record is returned more than once. However, in this case, we're still gonna leak something. We're gonna leak the communication volume, which means the adversary will be able to tell how many records we return from the size of the answer. So if we assume optimal efficiency, that we return the exact amount of information that is needed in order to answer a query, then this communication volume will always be leaked. And actually, all the crypto-based solutions right now, they leak this information. But everybody assumes that this is harmless. So if we hide the access pattern, just having the communication volume, probably it's not a problem. But is it? Actually, we have an attack even with the communication volume information. So how this algorithm works is as follows. So we are trying to build a table like that, where we are trying to find the number of unique queries out of all possible queries in the domain that return a certain amount of records. So in this case, for this data set, we have this query that covers the whole domain that will return 4 records. And we have also this query from 20,000 to 80,000 will also return 4 records. So in this case, we have 2 queries out of all the possible ones, unique ones, that give 4 records. Now, how many queries return 3 records? We can see that is this query, this one, and this one. So we have 4. And by continuing like that, we can find the number of queries that return a certain number of records. We can estimate this table well enough if we have t to the power of 4 queries, assuming a uniform query distribution. Okay? Now, it will be
if you knew
as
what the queries were,
previously.
they will give you more information?
Yeah, we need fewer queries. Just to retrieve all possible queries, if we can tell one query from the other, right? It would be t to the squared log n, log t, sorry.
Okay, so like t squared log t, okay.
Yeah, in order to be sure that we have retrieved all possible queries.
And it would just require you being able to compute equality between queries.
Yeah. Okay, so having this information, now we want to retrieve the positions of the records. We don't know the ciphertext now, we just know that there is a record somewhere in the domain. How can we do that? So, first of all, we assume that we have one record in a domain place which is after our whole domain, and one record which is before. And what we're actually trying to retrieve is not the exact positions of each record, but instead the distance between the records. In this case, the distance of these records from the previous one, it would be 2. R1 will be also 2, the distance between these 2 records. R3 will be 1, and R4 also 1. And now we can observe that essentially the number of queries we get for the queries that return 4 records can be computed if we multiply R0 with R4. So in this case, we had 2 queries that return 4 records, and we can see that R4 is 1, and R0 is 2. So it's like this query, and that's why this value multiplied by this value gives us this number. In the case of the 3 records, it's going to be R0 multiplied by R3, which is essentially the number of queries that return these 3 records, plus R1 multiplied by R4, which is the number of queries that return these 3 records. So this sum will be this value. And we can compute all these combinations until 1. For 0, the things are a bit trickier, but still we can compute it using the number of queries that return 0 records. And now the question is, having these equations, how can we find the values of the R's? The idea we came up with is that we're going to define 2 polynomials. And we're going to use these R's as the coefficients of these polynomials. So we have polynomial Rx, which is R0 plus R1x plus R2x squared, etc. And R reversed x, which is the same polynomial with reversed coefficients. So these 2 polynomials essentially represents the 2 solutions of our attack that we expect, the real one and the mirrored one. Now, if we multiply these 2 polynomials, we're going to get polynomial fx, which is actually a polynomial like this, which has coefficients, the numbers that we got from this table. And this is all the information we have, actually. So in order to find these R's, all we have to do is to use a factorization algorithm on this fx. And hopefully, we're going to retrieve 2 irreducible polynomials, each one representing Rx and the second one representing R reversed x. The question is that, do we always get 2 irreducible polynomials? So sometimes we might get more than 2. In this case, it means that we could have a different arrangement of records in the domain, which will give us the same table. This is a bad situation. But our intuition is that these cases are very rare, and we are trying to prove it actually this right now, and that even if this is the case, the number of solutions is going to be linear to the domain size. So there will not be a lot of data sets like that. And in order to demonstrate, in order to find out if this is true, we actually ran some experiments. So we used 2 data sets from the HCAP nationwide inpatient sample. Combined, we get 1,500 hospital data sets, each one having 6,000 patient records. So we assume that each data set has these patient records, and the index attribute where we ask range queries is the length of stay in the hospital, which has a domain size of 365, which is 1 year maximum. And by assuming uniform queries, we ran our attack, and we saw that for all 1,500 data sets, we're always having a unique solution. So probably our intuition is true that we probably will get unique solutions. So far, we've seen that if we are optimally efficient, if we return the exact number of records for each query, we can have reconstruction attacks. And even for weak adversaries, and even using just the communication volume. In real-life scenarios, an adversary would be stronger. So we should allow him probably to be able to control some data, to be able to know some query ranges and some answers, and even control the queries, be able to ask some queries. So the question is, if we relax the efficiency, this requirement, can we achieve reasonable privacy? So this is what we're going to see next. What we want to do is we want to use the notion of differential privacy in this case. So we want to apply differential privacy when storing records. And by doing so, if we can achieve that, then we can assume a very strong adversary who can choose data, who can control the data, and can also know exactly the query range, issue the queries, and know the answers. So how can we have the differential private storage? The general idea is that we are going to hide the communication volume of this information by inflating communication. So instead of returning the exact amount of records required, we're going to return a different amount, which is higher, and which will satisfy differential privacy. In order to do that in the atomic model case, where we have a ciphertext for each record, we're going to need to have multiple copies of the same record, multiple encryptions, or use encryptions of a fake dummy record in order to inflate the communication. So each time we ask a query, we can return the real records and multiple times the encryption of a dummy file. So differential privacy in general says that a randomized algorithm M satisfies epsilon delta differential privacy if the probability when this M receives as input our original data set and produces an output will be almost the same to produce the same output if this mechanism received as input a data set where one record was missing. This probability should be close enough within a factor of epsilon and within a constant delta, which is considered to be really small. If delta is 0, we say that we satisfy exact differential privacy. If it's not 0, we say that we satisfy approximate differential privacy. And a nice property is that any algorithm that takes as input the output of this differential private mechanism, its output will also be epsilon delta differentially private. So now we want to see how we can apply this notion to our setting. So we're going to use the sanitizers, as they are called, which is an algorithm, differentially private, that computes query answers. So let's say that we have a collection of statistical queries, let's say range queries or point queries. And we have this index, which is the information we use in order to issue these queries. And the mechanism will take this index and produce a data structure, which is a differentially private version of this index. So when we want to ask a query on the original data, we're going to retrieve an amount of records that we need. And if we ask the same query in this data structure, the differential private data structure, we're going to retrieve another number of queries that are needed, which we want to be close to the real answer. And for all possible queries, we want the difference of these two number of required records, of return records for this query to be within a bound of alpha. And there are works that show what is this bound, what is the value of this alpha, the required value. So, but let's see for each query class, what are the bounds? What are the, yes, sorry.
Why are you using BLR rather than something more efficient?
Come again?
Why are you using BLR, this mechanism, rather than something more efficient?
So this is like a general model. We're going to see for each query what are the efficient ones for each query class. Just wait and see this slide, OK? So, so for point queries, if we want to use pure DP, we can have alpha values equal to log t. If we use approximate DP, this is going to be constant. If we have range queries, we can have in pure DP alpha equal to log t, and with the approximate 2 to the power log star t. And for one-way attribute queries, we have these bounds. So we know how to efficiently answer queries in different classes, and now we want to use that on our system. So in order to do that, our idea is that we're going to use, first of all, ORAM in order to store our database. ORAM ensures that the access pattern is hidden. So when we ask a query, ORAM makes sure that we cannot tell if the same record is retrieved more than once. And then we're going to use the DB sanitizer for a specific class of queries, let's say range queries, in order to find out how many records we need to retrieve. By combining these two elements, we can have a general construction for differential private storage. So each time we want to answer a query, a range query, we're gonna we're gonna check the differential private data structure in order to see how many records we need to retrieve. And let's say for a specific query, we need to retrieve T records. Now, these T records, they have to be larger than the actual records we need to retrieve. So we're gonna use ORAM in order to retrieve the actual records needed for the query. And then for the difference, in order to satisfy the requirement of the differentially private data structure, it's gonna be by using multiple copies of the fake records. In this case, the efficiency in terms of storage is optimal because ORAM just needs to store each record once and one copy of a dummy record, a fake record. And the communication overhead is going to be alpha because for each query, we just have to send alpha more records, which is the error due to the differential privacy. However, ORAM is not very efficient yet. There are some implementations that are kind of efficient, but most of the systems don't want to use it. It's too heavy. So can we have a DB storage in the atomic model? We can actually, and let's see a construction for range queries. So the idea is that, first of all, we're going to split our domain into intervals which are disjoint, and we're going to consider each of these intervals as a bucket of records. So we want each of these buckets to store alpha records plus some copies of the dummy records. In order to determine the bounds of each bucket, and not to reveal any private information, we have to do that using a sanitizer, using differential privacy. So these bounds will not be accurate, will not include exactly alpha records. And in order to make sure that they have the exact same amount of records, that's why we're going to pad each bucket with copies of a dummy file. Now, we create a structure like that, and each time a query is issued, let's say we want to find the records of the clients that have account balance between 40,000 and 60,000, all we need is to do is to retrieve the records inside the buckets that cover this range. In this case, will be these two buckets. So as we can see, in order to store this information, we need to store some copies of the dummy record. And each time we ask a query, we need to retrieve probably more records than required, because if we ask a small query, let's say between 60,000 and 70,000, we'll have to retrieve all the records in this range. So we retrieve more real records than necessary, and we also retrieve copies of the dummy record. But we can bound that communication overhead. Now, can we have atomic differential private storage for one-way attribute queries? So we can, but the problem will be that currently it's shown that the lower bound for having that, it will gives us an increase in storage which is multiplied by k, where k is all the attributes in the data set. So this will not be efficient. So that's why we have some questions we need to answer. Could we relax the notion of the atomic storage? Can we relax some notions in order not to have these lower bounds and create atomic DB storage for one-way attribute queries? And what about two-way attribute queries? So in order to see the efficiency of our method of the atomic DB storage for range queries, we implemented on a real, using a real data set, which is the census from California. We have 500,000 citizens, which each one is considered to be a record. And we have a domain of 4,096 cardinality, which is the annual salary. And a range query will ask for citizens that have annual salaries between two values. So first of all, we have to determine how many buckets we're going to create. So we measure the storage and communication efficiency. The storage efficiency is the number of records we store divided by the actual number of records in the data set. And communication efficiency is the number of records we return in order to answer a query divided by the number of records required in order to answer this query. So the lower the efficiency number in the y-axis, the better the result. So as we can see, for the storage efficiency, as we increase the number of buckets, it deteriorates. And the reason is, because for each bucket, we have dummy records, encryptions of dummy records. So the more buckets, the more dummy records we need to store. And for the communication efficiency, though, things are a bit different. So when we have a very small amount of buckets, we have a very high cost in communication, because for small queries, we need to retrieve very large buckets. So when we have a small amount of buckets, these buckets are very large and they include a lot of records. So even if we needed just one record, we have to retrieve the whole bucket. So the communication explodes. Also, if we have a lot of buckets, we can avoid this problem, but we introduced more dummy records in the answer. Because for each query, we have to retrieve more than one bucket, which means more copies of dummy records. And we find that a nice trade-off is if we use 128 buckets for this data set. And this is what we use for our next experiment. So we fix the number of buckets to 128, and we run some range queries. So the different range cardinality here is a proportion to our domain size, 4096. And as we can see, the smallest the query range, the worse the communication efficiency, because we need to retrieve, again, a whole bucket in order to answer very small ranges. And as the range increases, the communication becomes closer to the optimal one. So to sum up, in this work, we identified the need to analyze the trade-off between privacy and efficiency for outsourced database systems. We saw that if we are optimally efficient, there are reconstruction attacks, even for weak adversaries. So this is not the solution, even if we use very strong cryptographic tools. And we presented the differentially private storage, which relaxes this optimality in the efficiency. We saw how we can have generic constructions, how we can enhance the ORAM cryptographic tool in order to also be differentially private. We saw some practical constructions with lower bounds in the atomic model case, which is very practical. And we implemented our attacks and some of the constructions to see their practicality. Thank you very much.